We're live.
All right, hello everyone. Thank you so much for joining us at for our next live session. We had to move it up by a little bit, and I will hand it over to Chris, who will get us started.
Okay, welcome everyone. Still talking to you from London and ready for your questions.
All right, our first question today, we are going to start with an email question from one of our students who asks. Astronauts from the Apollo mission have reported that lunar dust smelled like spent gunpowder. And the question is, what is the best explanation for the smell of lunar regolith?
That's a good question. I'm not sure I'm going to be able to answer that one, actually. I mean, the first part of the question that's of interest is, how did they smell the lunar soil anyway, given that they were fully sealed in spacesuits and were not supposed to be in direct contact with it? And the answer to that is that it's very fine regolith. The regolith just has a technical geological term for the sort of pulverized topsoil layer of the moon, essentially ground to the level of fine dust or almost talcum powder by micrometeor impacts, because the moon has no atmosphere. So the lunar, and there was speculation when Apollo went and the first people stood on the moon, there was real uncertainty relative to where they landed, whether they might sink in up to their knees or their ankles. Would it actually be a problem to move about on the moon if there was a lot of this powdery, pulverized soil? So it turns out that the truly pulverized talcum powder fine sand layer is only really an inch or 2 inches deep. So they would sink or crunch down into that. And it stuck to everything. So indeed, they were sealed in their spacesuits, but of course they went in and out of their spacecraft doing multiple spacewalks or lunar walks, and so the dust did in the end get everywhere. And yes, they did report that it smelled like gunpowder. So there's obviously nothing directly combustible with lunar soil. I mean, it's basically mostly quartz, and most of the lunar landings, it's quartz. They were in volcanic regions, typically, not exclusively. It's possible that pulverized quartz smells like gunpowder. I simply don't know. So I'm not actually able to answer that directly, but it was reported by the astronauts. And the reason they could smell it was not because they smelled it while walking on the moon, is because it got into the spacecraft and they smelled it on the way home. Ready for the next question.
All right, thank you, Chris. The next question is from a live viewer, Johan Geraldo, who asks, would you mind explaining entropy and the arrow of time? Is there any connection between the two or any similarity?
Supposedly, entropy is related to the arrow of time. Entropy in thermodynamics has a definition that was given by Ludwig Boltzmann in the middle of the 19th century. And in fact, the equation that defines the number of equivalent microscopic states, which is the sort of microscopic definition of entropy, is inscribed on Boltzmann's grave. Not sure where in Germany he's buried, but it's on his grave. I've seen the photo. So entropy is a colloquially stated measure of disorder of a system, and in physics terms, it means the number, it increases or scales with the number of equivalent microscopic states. So if you have a system where there are a large number of equivalent microscopic states, that is to say, states that are statistically indistinguishable in terms of their quantum properties, then that's a system with high entropy or disorder. Because obviously it doesn't matter how those objects or items or molecules or atoms are arranged, they always essentially look statistically the same. So, whereas something where there are very many different microscopic states has a very specific ordering, and of course is highly ordered. So entropy is related to microscopic states, and it increases over time because objects and things get mixed. So as time goes by, the properties of something where it might be stratified or separated will get mixed. The classic example of that is to imagine a sphere, a volume, where there's a gas on one side and a different gas on the other side, separated by a membrane, nitrogen on one side, oxygen on the other. If you remove the membrane, the random motion of the molecules will cause the gases to mix. And so starting from a highly ordered state, only nitrogen on one side, only oxygen on the other side, if you waited long enough, the gas would be fully mixed and the hydrogen and nitrogen would be equally found in each tiny region of that space. So that's a higher degree of disorder because the separateness of the two gases has been completely lost. So that's an artificial example, but there are many others. So in that sense, we imagine the process only goes in one direction because starting with a fully mixed gas of those two elements, you cannot imagine any situation whereby those gases would spontaneously separate back to anything like their original configuration. So that is a very graphic demonstration of the arrow of time because that process could only go in one direction. And there are many other examples like that. So yes, entropy is related to the arrow of time. Now, once the disorder gets very high, it's possible that the arrow of time may not be very obvious because a very high degree of disorder is not noticeably distinguishable from a very slightly lower degree of disorder. The only thing that's dramatically obvious to an observer is the difference between order and disorder. So when the entropy gets very high in system or a universe or some large set of objects, it's possible that the arrow of time becomes weaker, or the sense of forward and backward flow of events becomes weaker. That's just a speculation, though. Ready for the next question?
Excellent. Thank you, Chris. Our next question is from Sandra Gibson, who sent one in via email, who asks, are there stars old enough to have stopped spinning?
That's an interesting question. Probably not, actually, because the loss of angular momentum of it, well, there are stars, first of all, stars as they form do naturally have spin because the very slight rotation of a nebulous gas cloud, out of which a star might form by collapsing, spins it up. Now, once formed, a star will stay spinning. It's an object with coherence that doesn't change. And even as that star dies, its angular momentum is conserved. So if it collapses, then it'll spin even faster. So once the star is dead, whether it dies as a white dwarf, neutron star, or black hole, it will actually be spinning quite fast because it's a collapsed object at that point, spinning faster in a smaller configuration. And it will slowly spin down. It'll spin down through, if it's a very compact object, by gravitational radiation, like black holes and neutron stars emit gravity waves. And that loss of energy is also a loss of angular momentum. If it's in a region of space with other objects or gas or dust, then interactions with that other medium will gradually lose angular momentum as it transfers it to the surrounding medium. That's a very slow process. And so if you do a calculation, just say for a star like the sun, if a star like the sun dies, turns into a white dwarf, how long would it take the white dwarf that the sun leaves behind to stop spinning by viscous forces or interactions with the very thin medium between stars? The answer is, a very long time, many trillions of years. So it's likely that no star that's since died, or a star that is at the end of its life, is stopped spinning by natural processes. Ready for the next question?
Excellent. Our next question is from Black Bear Studio, who's on with us live, who asks, imagine that a gravitational wave is made visible, and here they say scaled up to visible size, but what would happen if that wave passed through an object? So what would we be able to see if we could see a gravitational wave and its effects?
So the gravitational wave is a wave that has various modes of vibration. So it's space-time oscillation, and that oscillation has different modes. It's called a tensor wave in mathematics, which means that it has different components of vibration and oscillation in different directions. It's not omnidirectional, if you like. Some of those modes of vibration and oscillation are like the sound waves, so they're compression and rarefaction, sort of the bunching up of space-time and then the stretching out of space-time. some of those modes are expansion and contraction. So the space-time in a plane getting bigger and then getting smaller again. So just imagine those two. Now in the gravitational waves that were detected by LIGO, the amplitude of those compressions and rarefactions, or stretching and compressing, are tiny. They're very, very much smaller than an atom. They're actually smaller than a proton. So the question is, what happens? Can you imagine scaling those up? Well, if you did scale them up, then obviously they would start to become dramatic. So you'd imagine space-time flexing at a level where you might actually see it with your eye. If the amplitude went up from 10 to the minus 15 meters to, say, a millimeter, that's still a very small number, but that actually might be visible or perceptible. If it became a centimeter, then yes, you could see objects literally squeezing and contracting as the wave passed through them. But you're having to amplify the real gravitational wave by a factor of 1 trillion for it to be visible. So that's the level you would need to amplify it for it to be visible, even hypothetically. Ready for the next question?
All right, the next question is from Siddharth, who is on with us live, who asks, China has announced the building of solar farms in space, and they say they might beam back the energy via microwaves. And the question is, but won't microwaves interact with the atmosphere or clouds or life or things like that? So, and we can talk about this in relationship to astronomy, I think, as well, and observations.
Right. So in principle, yes, you have to be quite careful with how you pick your wavelength. So it's true that if you pick microwaves that are short microwaves, so smaller than a millimeter, the atmosphere is opaque to them. They get absorbed by water vapor and other aerosols in the atmosphere. So you could not use those wavelengths. If you go to very long wavelengths of radio waves, like meter waves, then they actually refract in the atmosphere or sort of bounce off the atmosphere. If you're trying to send them in, and if you were trying to send them out, they bounce off back down. So there's a sweet spot there, and I think the sweet spot range is something like 5 millimeters to a centimeter. So when they talk about microwaves for this purpose of solar farms and beaming back energy, that's the wavelength they're talking about. And in that range, the atmosphere is transparent, so you could definitely focus the radiation and beam it back down. So the idea is huge solar collectors, sort of gossamer thin sheets that are preformed maybe by memory material into parabolic shapes where you can harness and collect from maybe square kilometers of collecting area and then beam it back down to the Earth in a concentrated beam. Now the energy density in that beam, if you do that, will be phenomenal. So that's a very dangerous beam of radiation, even though they're sort of low energy waves, as microwaves are. So there's a concern there that where would you beam them and how would you collect them? There's also technology that's not yet been developed for how you would even collect them, because to make sufficient energy density to concentrate a large amount of energy for useful purposes when you collect it at the Earth, you're also putting a huge amount of energy density onto a small collecting area on the Earth, which is likely, if you don't know what to do with it, to melt the material or vaporize it. So how you actually harness this energy once you've collected it and beamed down to Earth is still an unsolved problem, actually. One idea, there are various ideas. One idea, for instance, is to use it to vaporize metal or insert it into a superheated liquid, if you like, and then extract the heat from the liquid or from the liquefied metal. So there are various ideas how to do this. Very hypothetical. This technology is probably 30 to 50 years away from being realized. Ready for the next question.
Excellent. Thank you, Chris. So the next question is from Debaparna Goswami via email, but I believe that they are also on with us now. And the question is relating to clocks and gravity. So according to the general theory of relativity, time slows down near a massive gravitational object. So a clock would run slower near the Earth's surface and a bit faster at higher altitude. But the question is, if we think of a pendulum as a timekeeping device, shouldn't the period of the pendulum increase at a higher altitude and run more slowly because it's further away from the Earth? And is this a contradiction? And if so, why is it a contradiction?
All right, that's a good question, and it sort of gets to the limitations of timekeeping. So the realization of the relativistic prediction is of a timekeeping piece that is not mechanical. If you have a mechanical timekeeping piece like a wound spring or a pendulum, then it is not actually going to show the general relativistic effect. Apart from anything else, the precision of any kind of mechanical timekeeping device is many orders of magnitude too low to ever see the small relativistic effect. And then because it's a mechanical object, it's just subject to different forces, the gravity force, the force of whatever medium it's sitting in, that overwhelm anything you might see from general relativity. So basically, you can never see these general relativistic effects with mechanical timekeeping pieces. The way they're seen is with atomic or molecular clocks, and those are not mechanical. Essentially, they're using the intrinsic vibrational states of atoms or molecules, and those vibrational states are immune from physical conditions like pressure and temperature and so on, and density. And that's why, of course, they make very pure timekeeping pieces from which you can extract the general relativistic signal. The other reason you can extract it is they're incredibly precise. The best atomic clocks now are accurate at a level of about 1 part in 10 to the 17, which is an incredible precision. And that's improved a lot even in the last decade or so. And those clocks are actually so accurate, you can detect the difference in the speed of an atomic clock if you raise it literally by just a meter in the lab. That's how good the clocks are now. And those effects have been seen. That was published just about 2 years ago. So that's how you do it. Ready for the next question?
All right, the next question is from Pravya Agarwal, who's on with us live, who asks, how do we measure relative velocity in an expanding universe, especially when space-time is relative?
Right. Relative velocity is an interesting concept in an expanding universe. So the reference frame for all the observations is the expanding space-time itself. And we essentially need markers of that space-time. The space-time is invisible. It's a metric, if you like. It's a mathematical construct. And so the fact that the distance between any 2 points in space is increasing with time, that's what expanding space means, is meaningless if you don't have a way of marking that space. So on the larger scales, we use galaxies to do this. Stars are all bound into galaxies, so the largest units of matter are galaxies. And if you have galaxies that are well separated, they're all moving away from each other with the expansion of space-time. And so the relative velocities you measure are galaxy to galaxy relative velocities, or radial velocities, and you interpret those relative velocities in terms of an expanding space-time. Now, because the galaxies interact with each other gravitationally, they will pull on each other, and so they will deviate from the underlying space-time expansion, because you don't just have single isolated galaxies marching through space that you can measure this pure expansion. So when astronomers measure this expansion of the universe or expansion of space-time on any scale, it's kind of messy measurement because the galaxies themselves are interacting with each other. You can model that, though, if you know the mass of the galaxies, and these motions are called peculiar motions. So the astronomer term for the radial velocity component that's due to galaxy interacting with other galaxies rather than space-time expansion is called a peculiar velocity. So you measure the radial velocity, you have to infer what the peculiar velocity is, the gravitational induced component, and if you subtract that off, you recover the pure expansion of space-time, the Hubble flow. Thanks for that, and ready for the next question.
All right, our next question is from Jan Campos via email, who has a question about black holes. After crossing the event horizon, matter is described as being stretched or spaghettified, but that just seems like it's happening in one dimension. Are the 3 dimensions in time actually being stretched, or is space losing a dimension? Is a singularity one-dimensional? Why is that? Why are you stretched in one direction and not the others?
Yeah, it is. It's a little artificial to talk about spaghettification or one-dimensional. Um, so a black hole, like any gravitational object, a black hole will exert a tidal force, will have a stretching force. So if you're some distance from a black hole, um, the gravitation, the gravitational pull on your feet will be larger than the gravitational pull on your head, and that's the stretching force that would kill you as you approach the event horizon. Now that stretching force doesn't suddenly happen when you get to the event horizon. That is experienced all the way from a large distance from the black hole, and it just steadily increases as you move towards the event horizon. Now, because the lines, the tracks of matter falling into a black hole are obviously radial from the black hole, it's not simply one-dimensional because the black hole has a curved surface, and so objects are, if you drop particles in, they're following ballistic radial trajectories which will converge. So actually, in addition to the spaghettification or stretching, there's also a compression caused by the mass converging along these radial tracks towards the event horizon. That's a smaller effect, but it sort of goes against the simple spaghettification idea. So yes, you do have to consider it in 3 dimensions. Ready for the next question?
Okay, lots of black hole questions today. We've got a question from a live viewer, Predrag Ivosev, who asks, if not even light can escape a black hole, what are the jets of material that are blasting out as when black holes are usually depicted? Are they actually ejecting mass?
Right, so that can be a little confusing, and then we don't really see this. Okay, we do see this actually with massive black holes and quasars, radio galaxies and quasars. So you see pictures of those, and they have radio jets and optical jets sometimes. Um, but there are many artist representations of black holes, and they have an accretion disk, and then jets are coming out of the poles. So what's that all about? Well, it's not happening very close to the event horizon. So the event horizon still is an absolute boundary to knowledge and information. And any matter that falls in there at that point is lost from view or from space. However, on its way in, the matter is accelerated, and a lot of it, of course, because the angular momentum of the spinning black hole is swirled into an accretion disk. And from the inner edge of the accretion disk, it swirls down in towards the event horizon and is lost from view. But in the vicinity of the black hole, as it's falling in, because there's more of a vacuum or lower density at the poles, just because of the nature of the spinning object, then there's a path by which the plasma, the high energy particles, can escape. And in fact, you're using 2 forms of energy, using the rotational energy of the black hole itself, you're tapping the angular momentum of the black hole, and you're using the gravity power of the black hole. The gravitational potential energy is being transmitted into kinetic energy or radiation energy heading out along the poles. So there's a natural method by the geometry of the spinning object and angular momentum for material that's falling in or in the vicinity of the black hole to be accelerated away from the black hole along the poles. But all of this happens well outside the event horizon. If the Schwarzschild radius is the dimension of the event horizon, then the acceleration zone for black holes is typically 10 to 100 times the distance to the event horizon, or the Schwarzschild radius. So there's no violation of the fact that information can't get out of the black hole. This is all happening significantly further away. Ready for the next question?
All right, our next question is from Tony Gojanovic, who's on with us live, who asks, is Mercury's famed eccentricity due to gravitational effects or due to the effects of space-time?
Well, it's a combination. So Mercury does have an eccentricity, significant eccentricity of its orbit, more than most of the planets. And it's, of course, by far the closest planet to the sun. So that's primarily something that was put in place early in its formation, and it's not been completely regularized. So the eccentricity, the bulk eccentricity of Mercury's orbit is just a feature of its initial conditions of its formation. However, there's a much more subtle effect, which is, if you like, is a sort of epicyclic advance in angle of the nearest place of approach of Mercury to the Sun. It's called the precession of the perihelion, technically. And that was the effect that led Einstein, or that led astronomers, to see the effects of general relativity on Mercury. It's a very small effect. That advancing of the perihelion to Mercury is, I think, about 40 seconds of arc every century. So it's a very small, subtle effect. Needed very accurate observations to measure it. And it's caused by a general relativistic correction to what would otherwise be the Newtonian orbit of Mercury around the Sun. So the bulk eccentricity is a Newtonian effect and quite a strong deviation from circularity. The very much more subtle advancing of the perihelion is a general relativity effect and is really tiny and took a long time to even detect. But once detected, it was an affirmation of general relativity about a century ago. Ready for the next question?
All right, thank you, Chris. The next question is from Russ, who emailed us and is on with us live right now, who asks, the Earth is moving in orbit, but if the Earth's velocity was slower or faster, would that mean that aging would also be faster or slower? So we know that gravitational effects affect clock speed, but does the velocity of a planet affect clock speed?
I mean, the simple answer there is no, because the speed of the motion of the Earth, so the Earth has an eccentricity of its orbit of about 4%, so it does vary its speed as it goes around the Sun. But that is just a variation in orbital speed. So neither the orbital speed nor the spinning speed that gives us 24 hours in the day, actually affect how clocks work. Especially if they're not mechanical clocks, but even mechanical clocks are immune from that. The relativistic effects are due to something quite different. They're due to the actual gravity itself. So when the Earth varies in its speed in its orbit of the Sun, the gravity of the Earth is not changing because the Earth's mass and its configuration of its mass is not changing, nor when it spins. So really, clocks are not affected by either of those two parts of the Earth's motion. Ready for the next question?
All right, thank you, Chris. Our next question comes from a live viewer who asks, Propene asks, if the Sun was to disappear at this very moment, would we be thrown out of orbit instantly?
If it were to literally disappear, I mean, people have wondered what would it, if it turned into a black hole and you lost the radiation, but it was the same sized object, then the Earth would continue in its orbit. If the Sun were literally to be somehow, made to disappear in terms of its mass, then yes, the Earth would travel on a straight line in its tangential direction of motion. So just imagine you were spinning an object over your head on a string, and the string broke. You can imagine that the object would fly away in a straight line from the tangential place where the string broke. And the Earth, if the Sun disappeared, would do the same thing with its orbital speed of that instant. So it would not, its speed in a straight line away from its previous location would be the same speed it had when it was in orbit of the Sun. But yes, it would no longer be in a curved trajectory if that were to happen. Ready for the next question?
All right, the next question is from, again, a live viewer, Mr. Reapy1, who asks, is the James Webb Space Telescope worth it, even with the development of adaptive optics on Earth?
That's a question that astronomers ask themselves and each other because it's so expensive. James Webb has busted through all of its budget ceilings. It's a sort of too big to fail project at this point. I think it's actually hit $10 billion when all is said and done by the time it launches, because it's now not due to launch still for a couple more years after various delays and technical problems. Whether it's worth it or not really depends on the science it produces, but it does have unique capabilities. So I think it's not so much a question of the adaptive optics, it's a question of the large size of the telescope, the fact that it's going to work in the near infrared, the fact that it's a very cold telescope, so it will be extremely sensitive in the infrared. So I think James Webb Telescope's niche is not so much the sharpness of its imaging, although being beyond the Earth's atmosphere, it will have sharp imaging, but actually it's extraordinary sensitivity in the infrared part of this region of the spectrum, because it's a very cold telescope. And when you're on the Earth trying to do such observations, the thermal background, the fact that you're in a warm atmosphere, means your observations are far less sensitive. So that's really what its amazing niche is. And for that, maybe it is worth it, because we have no such capability on the Earth, and we never actually will. We need a telescope in space to be able to do that kind of sensitive infrared work. Ready for the next question? Oh, did I lose connection? Ready for the next question?
Oh, I'm sorry about that. No, it was my microphone. Our next question is from Marilyn Light, who asks, do you know how the sun rotates and its schedule? So how often does it rotate, and what do we know about the sun, or what can we learn about the sun from its rotation?
The sun at its equator, I think, rotates about every 22 hours, slightly less than every 24 hours. So that's ironically quite similar to the Earth, though the Earth is a much smaller object. But the sun, of course, rotates differentially. The sun is not a solid object, and so it rotates faster at the equator than at the poles. So that's the measure of how fast it rotates at its equator. And that differential rotation is important and interesting, because it means that the magnetic field inside the sun is gradually being twisted and wound up by its differential rotation. And that process eventually and slowly destroys the magnetic field and leads to the magnetic cycle, the sort of flipping of the poles in the solar cycle on a 22-year time scale. So the rotation of the sun and the fact that it's not a solid object actually is very important in the sun's behavior. Stars rotate at different speeds. There are many sun-like stars out there in space, and they do not all have the same rotational periods. Depends on their formation processes. We don't know if the sun is typical. It seems like it might be a slightly fast rotator compared to other stars of its mass and size, but it's certainly in the ballpark of the others that have been measured. Ready for the next question?
Excellent. Our next question is from Amri Baron, who asks, is the arrow of time that we discussed earlier real, or is it only in our minds? Is it possible that some alien species would sense time differently, or could other animals on Earth sense time differently from us?
Well, that's an interesting question, because of course it gets to the fact that the arrow of time has a psychological component. So one of the interesting things about the arrow of time, or time, is that at the level of microscopic interactions, there really is no arrow of time. Almost perfectly mirror symmetric interactions occur among subatomic particles. So the time axis is completely reversible, which is to say, if you see particles interacting and then leading to products after the interaction, in nature, you can either see or make to happen in the lab the reverse process in time, which means there's a time symmetry of these interactions. And it's foundational to quantum theory that there is time reversibility of particle interactions. So at the level of individual microscopic particles and the way they behave and interact, there is no time arrow. The time arrow seems to manifest when you have collections or aggregates of large numbers of particles. Is that necessary for the arrow of time? Is it impossible to have an arrow of time without large collections of particles? If you had a universe where they didn't gather together to form large objects, would time not exist? It's a very interesting question. We don't know the answer. The sense of time moving as something that cannot, this moving finger of time that never goes backwards, the river you can only step in once and never the same river again, is a very strong sense of perception that we have, a conscious perception. And it's a fair question as to whether we experience time in a way that's unique to our consciousness, to our intelligence, to our sentience. Since we don't get to compare notes with any other sentient creature we may share on the Earth, we share the Earth with creatures that may be sentient, perhaps elephants, dolphins. Other creatures are aware of time passing. We simply don't know. That would be fascinating to find out. So I think the jury is really still out on whether there's a psychological or sentient component to the nature of the way time is perceived, or whether it's all fundamental to the way the universe works. Ready for the next question?
All right, and just a quick clarification. Somebody caught that the rotation period of the sun is closer to 24 days as opposed to
Oh,
hours.
24 days. Right.
Um,
Good catch.
But we have a great question here from Keith, who is apparently a sixth grade teacher with a class in Mariposa, California. And one of the students would like to ask, can you explain the probability of another Earth-like planet sustaining life as we understand life?
Okay, it's great. Always happy to get questions from sixth graders. A good question too. We don't really know how to calculate the probability of life as we know it on an Earth-like planet. What we do know, however, is that there are many Earth-like planets. It's likely that there are between 10 and 20 billion Earth-like planets that are roughly habitable in the Milky Way galaxy. That's one galaxy. Now that's a large number, but as a fraction of a few hundred billion stars, it's not many at all. So Earth-like planets are still fairly rare. But that's millions that are possibly living planets. They have the ingredients for life. We think the chemistry is universal. If they're habitable, that means they're a star and their distance from the star is such that liquid water could exist, assuming they have an atmosphere to shield it and keep a blanket of radiation trapping it as a liquid. So those conditions do not seem to be unique to where we live. And then the question becomes, the probability now becomes, what is the probability given that kind of a situation or site that life actually arises? So you've got all the components. The chemistry is universal. There will be carbon, there will be water, there will be carbon molecules and some complexity that just builds naturally over time. Well, does that lead to life as we know it? And that is a truly unknown question. And it's the next big question to answer in astrobiology, basically, now that we know there are a lot of Earth-like planets. And astrobiologists are really struggling to know how to answer that question effectively because it's a very difficult question to answer. How do you know what life is going to be like if it's, say, not completely like our form of life? If it's microbial, but the metabolism is different. Maybe a metabolism that doesn't involve the production of oxygen, which is very easy to measure in a planetary atmosphere if you have the right instrument. Maybe it's microbes that produce methane, or maybe some other gas is involved in the metabolism. So given that we don't know what the nature of alien life might be, knowing how to detect it is very hard. And so we're going to have to try various things. But hopefully that question that you asked will actually be answered in about a decade, maybe 15 years, by careful observations of some few dozen of the Earth-like planets that we found. Ready for the next question?
Excellent. The next question is from Pedro, who's on with us live, who asks, can you tell us more about the ekpyrotic universe? How could a multiverse be the solution to the apparent fine-tuning of cosmological constants?
So the question alludes to a model, the ekpyrotic universe. Ekpyrotic is a Greek word meaning sort of eternal birth in fire. This is a sort of avant-garde, if you like, cosmology that's essentially trying to address the issue of the Big Bang and whether the Big Bang was the beginning of everything. In these ekpyrotic universe models, the Big Bang is not the beginning of everything. The universe actually emerges from higher dimensional states called branes that collide and interact, and occasionally when they collide, the energy that results from their collision spawns an expanding three-dimensional plus one of time, so three-dimensional space-time that we might observe to be our universe. But since these higher dimensional spaces pre-existed the creation of our universe in this model, there could be other universes. The universe could be cyclic. It could come and go. And so it's a fascinating model because it means the Big Bang is not a singular event that's the beginning of everything. There's other stuff going on, maybe in parallel and certainly before and possibly after our universe comes and goes. At the moment, there's no way to test the ekpyrotic model. It's a provocatively interesting cosmology that has some maybe conceptual support, because the Big Bang is a little awkward if it's the beginning of everything, because then you have no way to explain what caused it. This is attempting to explain what caused it, but there's no current observational support for it. So I would say it's a little niche in theoretical cosmology that gets some work. There was a group out of Princeton and Cambridge that did some really good work on it about 10 or 15 years ago. It still gets some work, but at the moment, as I say, we have no way to test it. Ready for the next question?
Thank you, Chris. Our next question is from Pravya, who asks, why do antiparticles always seem to get absorbed? Why can't a particle be absorbed and an antiparticle be emitted? And I think this also would be a good chance for you to answer some other people's questions about why, like what's the current state of, why is, our knowledge about why there's more matter than antimatter in the universe.
Right. So in the lab, matter and antimatter have an equal footing. And this is what essentially CERN does, Large Hadron Collider or similar particle accelerators. If you put a lot of energy into a small space, you can spontaneously, from that energy, create particle and antiparticle pairs. And you create them in equal numbers, because there's a conservation principle in physics which says that the particle and antiparticle pairs essentially balance out. They have opposite quantum properties. So if you started with nothing, you have to end up with nothing. And a particle plus an antiparticle in quantum terms, the math is that it's nothing. And of course, eventually the antiparticle annihilates with its opposite particle, going back to energy. So you have the cycle there. So the symmetry of matter and antimatter is pretty clear at the microscopic level, at the level of individual particles and antiparticles. They just have opposite quantum properties. But in the real universe, of course, we see an overwhelming preponderance of matter. Antimatter is created fleetingly in the lab and in accelerators, and that's it. We just don't see it anywhere else. We've ruled out antimatter on large scales very convincingly, because if it were there, it would annihilate at the interface with matter to create gamma rays, and we've had sensitive gamma ray telescopes for 40 years now. So there are no anti-stars, nor anti-galaxies, nor big chunks of the universe that are made of antimatter. That's pretty strongly ruled out. And so a physics and astronomy and cosmology question is why? Why is antimatter so rare? Given that at a microscopic level, it has equal rights, if you like. The current explanation is that this asymmetry, this profound asymmetry, emerged very early in the universe, when the 3 out of the 4 forces of nature, all but gravity, were merged into one superforce, grand unified theories, basically. So some tiny asymmetry in the combined forces led to a tiny asymmetry or inequality in the amount of matter and antimatter. A very small excess, in fact, not the dramatic excess of matter over matter we see. That very tiny excess would mean that early in the universe, when everything was hot and particles and antiparticles were turning into energy and then back into particles and antiparticles all the time, these particles and antiparticles would, for the last time as the universe cooled, annihilate, leading to radiation. And because there was a very slight excess of particles over antiparticles, we'd be left with a small residue of particles and a lot of radiation. And that would be the way the universe would be as it cooled and grew and expanded. And you stop being able to produce antiparticles readily from the hot, dense universe itself. And so that's sort of a natural explanation if you find a way to get this asymmetry in the forces of nature, a small asymmetry, of getting a universe that's overwhelmingly matter and, of course, a lot of radiation. So key to this explanation is that it accounts for, post hoc, if you like, the fact that there are about 100 million or a few hundred million photons for every particle in the universe, and essentially no antiparticles. Ready for the next question?
All right, thank you, Chris. Our next question is from a live viewer, Catherine Vogelvischer, who asks, I'd like to hear your thoughts on the Great Attractor. It seems like we heard a lot about it for a while, and I'd like to know what the current state of it is, what is it in general, and what makes it peculiar and especially interesting.
So the Great Attractor was the term for an extremely large structure of galaxies, a few hundred million light years away and a few hundred million light years across. So huge structure of galaxies, as big as a supercluster or even larger. It was first discovered in the 1980s, I think, early to mid 1980s, by astronomers who were doing galaxy redshift surveys. And they were the first astronomers to have surveys of tens or hundreds of thousands of galaxies. So they were the first really looking at large enough regions with dense enough sampling of redshifts to outline big structures. And what they saw was this large structure, which essentially was large enough to be pulling much smaller structures into it. And so the speculation was, based on observation of redshift and radial velocity, that our region of the universe, our local cluster, if you like, our local group of galaxies, and perhaps even the Virgo cluster into which we're falling, was being pulled in turn towards this great attractor. That's why they called it a great attractor, because it had a total mass of something like 10 to the 16 times the mass of the sun. That's 10,000 trillion times the mass of the sun, so incredible mass. Easily, obviously able to pull single galaxies or even clusters towards it. Now, the dramaticness of the Great Attractor sort of dissipated with time as people got better at doing redshift surveys. It turned out that the structure was not quite as well defined as they claimed originally in the 1980s. It wasn't quite as massive, and the tug it exerted on our region of space not quite as dramatic. There was a time at which it was thought that the Great Attractor, its existence itself, went against traditional cosmology, where structures have to form by hierarchical clustering over time, where small things form and then bigger things form. And you can only get something as big as the Great Attractor essentially hardly ever or at all in 14 billion years of evolution. So its existence was a problem for cosmology. But since the nature of the Great Attractor has shifted to it being less dramatic and less sharply defined and less massive than it used to be, I think it's not inconsistent with standard cosmology now. So it was an interesting landmark of the early stages of galaxy redshift surveys from 30 or so years ago. Ready for the next question?
All right, Chris, I think we're going to take one more question here before we wrap up. I know.
Yeah.
And so the question that we're going to end with is, we've had several questions about parallel universes, and we've talked a little bit about multiverses and things like that. So do parallel universes really exist? How certain are we on some kind of multiverse theory? Where are we on that?
I think the simple answer is that it's sheer speculation. The space-time and the expanding universe that we live in is pretty well measured by observations. We can see all the way to a horizon that represents about a distance of almost 40 billion light years in any direction, and obviously a time going back towards the Big Bang of just under 14 billion years. There could be regions of space beyond that, beyond our visible universe, and we simply there hasn't been time since the Big Bang, given the expansion rate of space-time, for that light to reach us. So it's certainly true that there are regions of space-time that might exist, and galaxies and so on, that we haven't had time to see, or the light hasn't reached us in the history of the universe. As for whether there are entire other universes out there, that's much more speculative, because the standard Big Bang does not accommodate them, does not really predict them, does not explain them. So I would say that the multiverse emerges from a very exotic speculation to do with quantum creation of the universe, where other quantum events might have occurred, and astronomers have struggled to find any way to test this idea. It still retains some popularity in the theoretical astrophysics community among some cosmologists who recognize that the universe did form in an inflationary situation where it was a quantum event, but that itself doesn't lead to anything we can measure. So I'm an observer, tend to be a little skeptical, a little hard-nosed about that, and I would put multiverse in the realm of pure speculation at this point. So thanks for all your questions, varied and interesting as always. And I'm going to be out of this country that I'm in now, Britain. I'm going to be in South Africa doing an astronomy and anthropology tour for a couple of weeks. So we'll pick it up in probably 3 weeks from now. Thank you and goodbye.
All right.
And thanks to Matthew and the crew who helped out. I can't see in the room, so I don't know who that was today.
No, I understand. Thank you very much, Chris. It's me, Matthew. We've got Victoria, and we've got Alexander, who's running all of our technical feeds. Also, I wanted to mention that we've had a couple of requests in various live sessions for a list of recommended books to read. And I wanted to let all of our live viewers know that we have seen those questions. We are not ignoring them, but we've just been trying to figure out the best way to deal with it. So I think what we're going to do is put together a recommended book or author list, and we will post that on one of our websites, and that way we can share the link instead of repeating those every week in a question and answer session. So we will let you know when we have that available and when we can share it with you. So thank you all very much and have a great day.